Okay, so today we're going to continue on in Module 5. We have a little bit of the first PowerPoint presentation to finish up. So what I'm going to do is I'm going to reopen up part 1 of PowerPoint presentation we had, and I'm going to scooch down to the last couple slides. Hold on, pressure angle. Spur gear selection. So we're going to be continuing on here with section 10.8, and that is going to be found on page 275 in your textbook, okay? And this section is looking at spur gear selection. So um, last time that we were together, we had looked at kind of looking at the relationships of gears and doing some calculations so we can get started on that layout work. But at this kinematic phase, or when we talk about kinematic design in terms of, or kinematic phase of, if you would, any design, as we know, it's that part before we're worried about the forces. So in the last time we were together, we started a nice handy dandy equation sheet. Okay. And here you'll notice that we have the relationships between diametral pitch, pitch diameter, and the number of teeth. And this helps us to determine what is the physical size of not only the teeth, but also the gear. Okay. And once we have the physical size of a gear and we mesh it with another gear, another element that we're interested in these early phases of the design process are going to be, okay, how much space do I need to account for this? So center distance is another essential item that we're going to need, if you would, to lay these things out and make sure they fit within the confines of the space that we have to work with. Okay, so we had a couple different options there for that. Now, we then looked at, okay, when we're looking at the physical sizes here, what is the velocity ratio between two gears that are in mesh? So two gears that are in mesh, we're going to have a pinion, the smaller one, and we're going to have a gear. And we want to know, okay, how many times does that pinion, the smaller one, have to go around in order to get that big one to go around just one time? And we have a couple options. We can either work with the angular velocity or the, if you would, RPMs, the speed, the rotational speed of each one of those gears, one being the pinion, two being the gear. Or we can use their physical dimensions, diameter, number of teeth, and radius, okay? So any one of these becomes available to us depending on the information that we have to calculate a velocity ratio between two mating gears, okay? Now, additionally, we looked at, okay, if we wanted to determine what the pitch line speed was, or in the applications that we saw for the example that we did, which was a grocery conveyor, a grocery line conveyor, pitch line speed ends up being, well, how fast is that belt going? Okay. So that relationship was familiar to us because this was a repeat or a reapplication of looking at when we have something that's going around, a fixed center and it's rotating at a certain speed. What is that straight line velocity out at the edge? This we learned in Module 4 when we were looking at velocities of points on 4-bar mechanisms, okay? So this was a reapplication, okay? So over on the right-hand side then was just the definitions and the units and stuff that we would be expecting. So like I said, kinematics is all about what are those first phases of the design process that I need before I'm worrying about forces. Notice we're not worried about, how much force is here, what is the stresses on it, anything like that. We're just looking at right now layout and, how fast things are going. Okay, how fast things are going. Now, after we kind of know where we're at in terms of, the space that we have, now we have to actually pick the gears. In the problems that we were looking at previous to this, that was already specified for us. And the word problem would give us, how many teeth or what was the diametral pitch. But as a designer, sometimes we're starting with a blank piece of paper. And here is our application. So what we need to do is I want to show you how you're going to be able to pick an appropriate diametral pitch. And remember, diametral pitch is that size of the tooth. Okay, I'm gonna peek back at kind of the beginning of our chapter here, where we had that really nice illustration showing typical numbers of diametral pitches or sizes of diametral pitches. It's at the top of page 263. You don't have to open up here because we did look at this last time. But remember, diametral pitch, capital P sub D, is going to let us know how large or small that tooth is. So if we look at the larger numbers up here, those equate to smaller teeth. Down at the bottom, the smaller numbers mean that we have bigger, chunkier teeth. Okay. Now, as we kind of look at these sizes, kind of in the middle here-ish are like those typical industrial applications like conveyors and gearboxes, stuff like that. Up at the top here, this is going to be things that have less stress on them. And I think I mentioned last time, maybe, printers, the gears that are in there. Down at the bottom, we're probably looking at things that are going to be much higher torques and forces like machine tools or, bridge type of application or cranes that are going to just see higher forces and higher stresses. Okay. But our job as a designer is for our application, which one do we pick? Okay. So that's going to be part of these early phases here. So diametral pitch. So now that we've talked about diametral pitch, we have to be sure that when we have a set of mating gears, the diametral pitch has to be the same. We had talked about that last time. That's the profile of the tooth. So if I know that I'm going to pick, for instance, a number 8 diametral pitch, both of my gears have to have diametral pitch of 8. Okay. Additionally, they have to have the same pressure angle. We talked about the 3 pressure angles when we were together last time, and we did talk about it in terms of forces. I'm not going to repeat that, but remember there are 3. There's 20 degree and 25 degree. Those are the ones that we're going to specify for any new designs going forward. Okay. But out there are 14.5 degree pressure angles, and those are for service parts and maybe designs that you have to maintain out in the field. But anything new, you want to design with 20 or 25, okay? And then lastly, we're going to be specifying the number of teeth. Now, the number of teeth does not have to be the same for each one of the gears. Actually, they're always usually going to be different when we want to slow things down or change the speed between one gear and another, as well as increase or decrease the torque. The torque discussion is going to happen when you guys are in machine design elements, which is going to be next term for you if you continue kind of in the sequence of classes in the program. So number of teeth, pressure, angle, and diametral pitch all have to be specified for each one of our gears, with the diametral pitch and the pressure angle having to be the same when we have 2 gears in mesh. Number of teeth obviously is going to be most often different. So we've already talked about diametral pitch, kind of redefining it, if you would. Remember, diametral pitches variable is going to be that capital P. Okay. And it says here it's the first parameter that we select when we're specifying the gears. So how do we do that? Well, we're going to use table 10.6 in our book to get us in the ballpark. Now, as we look here, I go underneath. On page 275, you're going to notice this table 10.6. And this is titled Suitable Diametral Pitches for 20 degree mild steel gears with a standard face width. Okay, so these are going to be, if you would, standard gears, just like the fastener industry. As we had mentioned the last time we were together, the American Gear Manufacturers Association kind of governs these standard numbers. Okay, so you're going to notice that the numbers on the inside here are going to be the diametral pitch, the standard diametral pitch numbers that are on that list, okay, as deemed by the American Gear Manufacturers Association, okay? And then anybody who is manufacturing gears and selling them, they're going to be, making and focusing on gears on this list, okay? So diametral pitch for instance, if I have to know what my pinion RPM is. So we typically refer to that as the higher speed gear. And the higher speed gear is usually going to be the one where the input is coming in, and it's also usually the smaller of the two. Okay, so the pinion is what we refer to that as. So that's going to be the pinion RPM. So up here, you're going to notice that they list like typical RPMs that we might see. It might not be a complete exhaustive list, but these are kind of the main numbers. So if I have, for instance, 1800 RPMs for an application, which was the one that we saw, I believe, for the cement mixer. Was that? Oh no, it was for the grocery conveyor. It was 1800 RPMs. I'm going to say, all right, so my opinion is 1800 RPMs, but then I also need to know how much horsepower is going into my application. Motors or anything that has an input is going to have a horsepower rating. And a horsepower rating is the ability of the input, the motor, to generate work, okay, that is going to occur. Again, these are kind of those force types of things, but we will usually have, or we will have for an application, what is the horsepower that is being generated or going into our system. So we've got to pick that number here. So for instance, if I have 1800 and let's say I have I just don't want to pick what we have for the other one. Let me peek ahead here. Okay, good. So if I have 1800 RPM on my pinion, and let's say I have a half of a horsepower motor, okay, that's going to be going in there. What I want to do is I want to find the number where I see the intersection between those two. Okay, so in this case, you'll notice that the number 20 is there, the number 20. So if I go back to my list here of diametral pitches, and I look, you're going to notice that a diametral pitch of 20 in comparison to these other ones would be a standard diametral pitch or a size of a tooth that I could pick. Okay. If we let's say stick on that 1800, but we increase the amount of horsepower, let's go up to 1. Notice that, well, of course it stays on 20. Let's go to 1.5. Notice that now we go to a number 16. Okay. So they're gonna have teeth that are gonna cover a range. But notice that as I went up in horsepower, my diametral pitch numbers get smaller. Okay, so horsepower, like I said, is the ability to do work. So as those numbers get smaller, my teeth start to get more chunky because now it's expected to do more. Okay, does that make sense to everybody? Okay, just to kind of see that relationship. So diametral pitch, the size of the tooth, those are going to be integer numbers that are a standard set of numbers that correspond to, how large or small that tooth is going to be. Now, this chart right here gets us in the ballpark. Just like anything, we don't want to just randomly pick a number out of the air for no reason, okay? So what this does is it takes that RPM of our faster moving shaft and whatever the horsepower is for the application that we're using, and now it like says, okay, we're going to use a number blah, blah, blah for our diametral pitch, okay? And that's where we start, okay? Now, we're going to qualify this design and we're going to make sure that it's okay by taking it to the next steps further, which are going to be, like I said, in machine design elements. That's when we determine what are the forces that are here, what are the stresses this is going to see. And sometimes we may need to alter this number as we get further down the line in the design process. But this is just a starting point, just so that you know. Okay, we're not like committing to the number of gear here. We're not like married to it at this point, but it's a place to start our calculations. Okay, so that's where we're at, if you would, in the design process. So that's table 10.6. Then what we're going to do is we are going to talk a little bit about pressure angle, which we already did. Again, going forward, we're going to have 20 and 25 degrees. 14 and a half are going to be for replacement parts. And like we said, gears have to that mesh have to have that same number of teeth. Or I'm sorry, same pressure angle. And then as we look at number of teeth here, we've already mentioned as well. The other thing that we have is we're going to look at table 10.7. At the bottom of page 276 and then the top of page 277, you're going to notice that we have the chart that we have here. It says the number of teeth for commercially available stock gears. Now, you're going to notice that each one of these sections has a category which sets it up for what is the diametral pitch number. So it starts with a diametral pitch of 32, 24, 20, and all the numbers that are listed below in that section are the number of teeth that you can expect a gear manufacturer to make a gear out of. So for instance, they're starting here with 12, then they're going to 14. There's not a 13 in between. Now you might say, why is that? I'm going to say, I don't know. I don't know. They just don't make every single number of teeth. Now, does that mean you can't have it made that way? No. It just means that if you want to get something off the shelf, commercially available, which usually means that they're less expensive, just like anything that's not custom, right? Then it's going to be available for you. Okay. And that's usually where we want to start, unless there's a really good reason why we would not want to use a number of teeth on the list that we have here. We want to stick to what is commercially available. Again, it's going to be less expensive and they're going to have a lead time that's going to be much less, or, off the shelf, if you would. As we move to the next page here, it continues that list with more diametral pitches and then the number of teeth that are available on a standard gear in each one of those categories. Okay. All right. So now let's look at example 10.9. Okay. And we're just going to do it together. This is very, I don't know, short, this particular example, but then we'll do another one where we get further. So number 10.9, we look underneath. This is on page 276. Okay. And it's right in the middle of the page here. Okay. Example 10.9. So we have a pair of mild steel gears to be selected for the concrete mixer application that we did in the previous problem. It was actually in 10.3. We did this problem earlier. The mixer is driven by a 10 horsepower engine, and the speed coming from that engine is 1800 RPMs. They want us to determine the appropriate diametral pitch. Okay, so this is going to be one of the practice problems that you hand in. So we are going to start here. This is example 10.9. Okay. And what we're given is horsepower is equal to 10 HP. And then our angular velocity of our pinion. So I'm going to call this W1, okay? Because ones are pinions, twos are gears, as we're specifying here in this chapter. And that's equal to 1800 RPM, okay? So these are, if you would, our given quantities, all right? What we want to find, okay, is going to be our diametral pitch, okay? What is the size of the tooth that I want to use, okay? So I'm going to go to that chart or that table 10.6, and we're going to use the 1800 and the 10 horsepower to find, okay, what is an appropriate diametral pitch? What is an appropriate size of a tooth, okay? So here you'll notice that this is that table 10.6. Again, it's on page 275. We're going to go over to the top here where it says 1800 RPMs. And we're going to find where we have 10 horsepower going down, and we're going to see where those meet. So 1800 is this column right here. So it looks like by lining those two up, 1810, we're going to get a diametral pitch of 8. Okay. And again, this is our starting point. We are in those early phases of the design. So this is where we're going to start things off and, do our calculations and then qualify it with more information as we go along. So then I'm just going to say from table 10.6, and I'm just going to list the page 276, diametral pitch equals 8. That's it. Okay, because it's really just reading the value from that chart. So that's what I want you to identify for this practice problem. Okay. So it's just getting you, getting you started on how do I read that chart? So any questions on that? Kind of easy peasy, right? Yeah. Yeah. Okay. Cool. Now, the next example we're going to do is going to be a little bit more involved. It's going to take it further, if you would. And what we're going to do is we're going to actually select a full set of gears, two gears that are going to mesh with one another. And this is our example problem 1010. This is going to start at the bottom of page 277. And you're going to notice that it's right below that chart. So it's right here, example 1010. So it says we have a gear reducer is used on a concept for a small trolling motor for fishing boats. The gears must transmit 5 horsepower from an electric motor at 900 RPMs to the propeller that needs to go 320 RPMs. Select a set of gears to accomplish this task. Okay, so our input is going to be 900. Our output is going to be 320. Okay, now we've got to specify, we don't have anything here. It's not telling us the number of teeth. It's not telling us the diametral pitch. So we've got to pick all that stuff just from just the information that we have here. So it's kind of an open problem. So the first thing we need to do is, because we need to pick out the gears that are going to be in mesh. And if we just look above here, this chart was, what are the commercially available number of teeth for each one of the size of tooths that we have here? So in order to use, to figure out how many teeth we're going to need, we first have to know what is the diametral pitch that we are going to be dealing with, okay? Which means that first things first, we've got to pick it off of our diametral pitch table, okay? Notice here that this is for 20-degree mild steel gears. So that's what we're going to be using, okay? So as we start out here, for example 1010, example 1010, okay? We want to find, okay, or specify a set of gears, right? So we need, number one, the diametral pitch, okay, for each gear, the set of gears, each of it's going to be the same. We also need to find what is the pressure angle, okay, for each gear. And then we need the number of teeth on the pinion and the number of teeth on the gear, okay? So this is pinion, number 1, and gear is going to be number 2, okay? So that we can then say, okay, here are the 2 gears that we're going to need to go from 900 RPMs to, I don't really need a number there, to 320. So our givens then, right? Our givens, usually I do givens first, but we'll do givens second here. We know that our application, our angular velocity of our pinion is 900 RPMs from the problem. So this is the pinion. Okay. We know that we want to, if you would, slow it down or gear it down to 320 RPMs. And that's going to be on the gear. So we're going to have 2 gears that are in mesh. The faster, smaller one is going to be going at 900 RPMs. The larger, slower one is going to be going at 320 RPMs. Okay. And then the other piece of information, we know that our horsepower rating is, what did it say? 5 horsepower. Okay. All right. So as we said, the first thing we have to do is find that, that diametral pitch. So step number 1 is going to be finding the diametral pitch. Okay. And that's going to be the same number for both. So we're going to use table 10.6 again. Okay. And again, this is on page, just if you need to go back and reference this for your homework. Sometimes I like to put these on, especially if you need to reference back to a particular chart. We're looking at table 10.6. So we want to find our 900 RPM column. Okay, I circled it at the top here, and the 5 horsepower row. And where those two come together, notice that our diametral pitch is going to be 10. Okay, so that's the size of our tooth. Okay, so P sub D is going to be equal to 10. All right. Then the next thing we need to do is we need to determine the pressure angle. Okay. Now the pressure angle was kind of determined for us. Okay. Because on that chart, by using that chart, it says it's 20 degrees. Okay. So we're just going to say our pressure angle equals 20 degrees. And that's from table 10.6. Okay. If table 10.6 was saying that it was a 25-degree pressure angle, then we would have to do that. But it's a 20-degree pressure angle. Okay, so we can put a box around this if you would, and that's just from that same table. Okay. All right, then the next thing we need to do, and this is going to be the more involved part, this is going to be determining the number of teeth on each gear. Okay, number of teeth on each gear. Now, the number of teeth on each gear, we are going to be picking from our standard table 10.7. Okay, 10.7 starts at the bottom of page 276 and it continues on to the top of page 277. Okay, now because we picked a diametral pitch, or the table told us diametral pitch of 10 is what we're going to be working with. So that means that these are the numbers of teeth on the gears that we're going to have to pick from to accomplish 900 RPMs to 320 RPMs. Okay. Now, because we have that difference of 900 to 320, we need to first identify what is that velocity ratio, right? Okay. And then what we'll be able to do is we'll be able to use that to help us determine the number of teeth and such. So velocity ratio. Velocity ratio, remember, I can calculate it using a couple different things. Let's see, what's my thing? Okay. If you remember from our equation sheet, velocity ratio has a number of ways that we can calculate it. So the first one that we see listed here is the angular velocity between the pinion and the gear. Okay, we have these, right? We know what these are. Our input are 900 and our 320. Okay, so we can calculate it using that. If we knew any one of the other ones, we could do it. But because we don't know the number of teeth yet, we can't determine the diameter. We can't determine radius. So really, this is where we're gonna start. So let's calculate our velocity ratio using this angular velocity of the pinion divided by the angular velocity of our gear. Now, this is a ratio. So we're going to have the same units top and bottom. We know from our problem that the pinion, the input, is going to be going at the 900 RPMs, and that the gear is going to be going at 320 RPMs. Putting your units in here, notice that they cancel top to bottom. Our velocity ratio is always going to be a number that is unitless, always, okay? So our velocity ratio here is what?
.8125.
Yes, 2.8125. So 2.8125 and no units here, all right? And this is not a final answer. This is just going to be something that we're going to kind of use along the way here. So what the velocity ratio tells us, remember, is how many times our pinion, our smaller gear, needs to go around in order to get that gear to go around once, okay? So what we're doing is we're reducing our speed here by a factor of 2.8125, okay? Now, we need to find number of teeth, okay? Now, as we look back here, if we notice, velocity ratio can also equal the number of teeth on the gear divided by the number of teeth on the pinion. Okay, number of teeth on the gear by the number of teeth of the pinion. So I'm gonna just go a little bit further down here, and if I look at those number of teeth, because that's ultimately what I want to know, like, right? I want to pick what are the number of teeth in the pinion and the gear for this set. So I'm going to say velocity ratio is also going to be equal to N2 over N1. Okay. Notice that N1 was on the top, or W1, number one was on the top on the previous step, but now 2 is on the top here. The larger number always has to be on top, just so you know. And when we look at physical sizes or number of teeth, the gear always wins on those. But speed, the pinion is going to be the one that's on top. Okay. So now we know that our velocity ratio is 2.8125, right? And our number of teeth on our pinion, which is number 1 here, is in the denominator. What I want to do is I am going to multiply my N1, number of teeth on my pinion, up times the velocity ratio. So I'm going to rearrange this, and I'm going to say N1 times 2.8125, putting the number in here now, is equal to N2. Okay, is equal to N2. Now, what this is going to offer us is the ability to try out some pairs. Okay, and we're going to be looking and using our table of standard number of teeth on our gears. Okay, so what we're going to do is we're going to say, okay, let's go in our section 4 diametral pitch of 10. And let's start by looking at, the lower numbers here. Okay, remember the pinion is going to be the one that is going to be the smaller gear. So this is going to be our N1. So if we pick any one of these, for instance, if we say, all right, how about we start with the number of teeth of 14, okay? Let's just, and this can be a designer's decision. So when N1 is equal to 14, okay, that means we're going to have 14 times 2.8125 is going to be equal to N2. And actually, I didn't put my units in here. I'm sorry. I want to do that. It should be 14 teeth times 2.8125 is equal to N2. Does that make sense to everybody? Put your teeth in there or the units, because otherwise when we do this, there's going to be no units. You're going to be like, what are they? They are teeth. Okay. So now we're going to take 14 and we're going to multiply that by 2.1875 or 2.8125. Okay. And you're going to notice here that we get 39.375 is equal to N2. You guys get that same number? Yeah. Now, if I look at this number, 39.375, that means that I have to have 39 whole teeth, but then 3/8 of 1 tooth. Can I make a gear with a partial tooth? The answer is no, no. So I have to have an integer number first for my N2, and I also have to make sure that it's on my list. So an N1 of 14 is not going to work for me, okay? And this is what we do. So now we're going to try, okay, let's try N1 equal to, let's go back to our list here, and let's try N1 equal to 15, for instance, and let's see if we can get a good number. So equal to 15. So we're going to take 15 teeth times that same ratio, 2.8125, and we're going to find out, okay, what is the number of teeth on a gear that I need for that one? So 15 times 2.8125. And here it's 42.1875, right? Is that one going to work? Without even looking at our chart? No, because I've got this decimal, so that one's not going to work, okay? Now you might say, but if I use 42. And if we look here, is there a 42 in that section? There is not. So even so, that whole number is not going to work, because you might say, well, if I get close, is that okay? The problem doesn't say getting close is okay. So we continue on. So our next one is going to be N1 is equal to 16. So then we're going to take 16 teeth times 2.8125, and we're going to see what we get for N2. Oh, look at that. We get 45 teeth is equal to N2. This is a, something that we want to pursue. So it's a whole number and it's 45. And then we have to look, is 45 available as a diametral pitch of 10? It is. It is. So 16 and 45 are going to be a good pair for us. Okay. And they're going to get us exactly the velocity ratio that we need. So we can say that N1 equal to 16 and N2 equal to 45. And I should put teeth here. I'm sorry. I should have put that in there. Teeth. Okay. This would be a good pair. All right. This would be a good pair. All right. Now you could continue on. You could continue and say, all right, let's check, the next one. You could say, okay, maybe we want to have a plan B and say, okay, let's see if 18 works, if 20 works, and so on. Okay. But we're going to see if this is going to work for us. All right. So we've got two valid values here that are off of our chart that are standard options for us. And now what we want to do is we want to find out, okay, what is the center distance between these two? Because that'll help us to know if it's going to fit into our layout. The problem didn't give us any sort of, envelope that we had to work in, but as a designer in the real world, if you would have, some idea of how big or small this could be. So let's go ahead and, as the last step here, calculate, just like the problem did, the center distance. So step number 4 is going to be center distance. Okay. So C is equal to. Now, what we know about our set of gears that we picked is we know the diametral pitch, and we now know the number of teeth on each. Okay. Number of teeth on each. So what we can do is we can look back at our center distance equations, and we can determine which one would make the most sense. Okay. So we didn't individually calculate the diameters yet. We could do that with this relationship up here, because now we know the number of teeth and we know the diametral pitch. We could calculate the diameter. But if we want to just jump right to center distance, we can use the number of teeth in each and divide by 2 times the diametral pitch to get the center distance directly. Okay. And that's the one that I'm going to use. So I'm going to say N1 plus N2 divided by 2 times the diametral pitch. So this is going to be 16 teeth plus 45 teeth, okay, divided by 2 times 10 diametral pitch. Now, remember, they'll specify diametral pitch as just a number, but we know that there are actually units associated with it that are teeth per inch, okay? So we're going to put in not teeth, teeth per inch. Okay. So as we look here, these teeth on the top, when they combine, they're going to cancel out the teeth on the bottom. And the inches is in the denominator of the denominator, which means that it multiplies on top. So our units that are left over are inches for a center distance. Does that make sense? Yeah. Yeah. So now go ahead and take 16 plus 45 divided by 20. And see what we get here. Should get a value of 3.05 inches. Do you guys get that same thing? Okay.
Yep.
Yes.
Yeah, excellent. So that would be the end of the problem then. So this number you would then, as the designer, and again, they didn't give us any envelope to work within, but you would know, is this okay or not? And if it's not okay, you would go kind of back to that set of gears again and see if there's another set that we could work with to achieve that 900 to 320. Okay. So questions on that? All right. So if we go back to our PowerPoint presentation, it looks like that takes us to the end of where we're at. So now that really completes, if you would, part one of the gear design. Now we're going to move into looking at gear trains, which is the if you would, the part two, the final part of this particular module. So I'm going to stop our recording here.